All right, now we'll talk about the SN1 reaction. I'm going to go through it a little bit quicker just because we've already talked a lot about this stuff for the SN2. The SN1 is exactly like SN2, except everything is the exact opposite. All right? It's a unimolecular reaction where that the reaction only depends on the concentration of your electrophile. Okay, I'm sure we'll talk about that. You have a carbocation intermediate. You actually form an intermediate. Okay, the rate is just dependent on the alkyl halide, like I just said, not on nucleophile. You can change the concentration of your nucleophile all you want. It does nothing to the rate of the reaction. But if you double the alkyl halide concentration, you double the reaction. If you half the alkyl halide concentration, you half the rate of the reaction. Okay, you get racemization in this case. Remember, racemization is you have 50-50 RNS. So you lose all stereochemistry. Okay, last chapter, on the SN2, you get 100% inversion. Here you get no inversion. You lose everything. Okay. In this case, it's a two-step mechanism, or what's called a stepwise mechanism. All right, what happens first is your leaving group leaves and you form a carbocation. Now remember what we talked about? Tertiary carbocations are more stable than secondary, or more stable than primary. Notice this is the exact opposite of what we had for SN1 for SN2s. SN2s was the other way. This is the opposite because you're forming a carbocation. In fact, you don't even do primaries with the SN1 mechanisms. It's not going to happen. Once you form the carbocation, your nucleophile can come in and attack it. All right, if the nucleophile is an uncharged molecule like water and alcohol, the positively charged product must lose a proton. Okay, we'll talk about that. So here's the basic mechanism. First, this is what is considered the rate determining step. All right, remember your concentration is based on how quickly this halogen is going to leave, because your rate is just dependent on your electrophile. So the faster your halogen leaves, the faster the reaction goes. So first step, halogen leaves to form a carbocation. And then your nucleophile, notice this is a weak nucleophile. Notice there is no negative charge here. See that? This is a weak nucleophile. Okay? It comes in here, forms the bond. Notice we have this hydrogen sticking out with a plus charge. So your base, your chlorine, what is going to happen is the halogen that left, which is an iodine, is going to come over and eventually pluck the hydrogen. I do not know if that mechanism is on these charts, but I'm going to write it there. If you're confused, we'll go over it in class. Okay, nucleophile attacks the carbocation forming the product. Oh, there it is, perfect. They have the methanol grabbing it, but you can actually have the I-, like how I had in the last slide. It's either the methanol or the I-, whichever one makes most sense to you is fine by me. Okay? So that is the last step of the mechanism. Energy profile, notice we have an intermediate in this case. We do form an intermediate with the two transition states. The rate determining step is the first transition state. Okay, forming the carbocation is endothermic. Okay, but the overall reaction is exothermic. The step 2 is fast with the low activation energy. All right, the rate, again, like I said, tertiary is faster than secondary, faster than primary. More stable carbocation requires less energy to form, so the reaction is going to go faster. Okay, note, look, it even says here, opposite to SN2. Man, this author thinks just like I do. All right, better leaving group will increase the rate. Again, you still want a good leaving group. Okay, this is why you get racemization. This example is why you get a racemic mixture. Let's say we're starting with 100% S. Well, what happens is once your bromine leaves, you form a planar molecule. You notice I have a tetrahedral molecule here. This is tetrahedral. But then I get a planar molecule because I form this carbocation. Carbocation is this perpendicular p orbital. This goes planar. So now my nucleophile, which is ethanol, notice can attack either from the top or it can equally attack from the bottom. There is no preference. Remember in the SN2 case, your nucleophile had to attack from the backside. Your nucleophile has to attack opposite your bromine. There's no other choice. But in this case, it is free to choose whichever side it does, and it does. Based on statistics, it equally chooses, both sides. So that's why you get both the R and the S enantiomer, and you get 50% of it this and 50% of it that. So you lose all of your stereochemistry. Okay, so carbocations are sp2 hybridized and trigonal planar. The lobes of the NTP orbital are on both sides. The nucleophile can attack from either side, producing mixtures of retention and inversion of the configuration. All right, so you lose all the chirality. Carbocation stability, we've talked about this. Hyperconjugation, we've talked about what hyperconjugation is. This is kind of a perfect little, you remember it was the hydrogen, the bond from the hydrogen here sharing its electrons into the overlap. I don't know why they have the slide here. We talked about this in chapter 4 already. Stereochemistry, not sure why they're doing this. We already did this. You get both sides. It's just extra slides. Can never hurt to have extra slides. So there you go. SN2 reaction produces mixture of enantiomers. There's usually more inversion than let's not worry about that. One thing that can happen with SN1 reactions is what's called rearrangement. Anytime you form a carbocation, you can get rearrangements. I'm going to put that here. Rearrangements, carbocations. Because we're going to keep seeing this all throughout the semester. Anytime you can form a carbocation in the intermediate, you can have a rearrangement. So what's a rearrangement? So you would expect, if you're doing this reaction, this is an SN1 reaction. How do I know? Weak nucleophile. Notice that is weak. This is a secondary carbon. Okay, it's weak because it's protonated. Okay. So what's happening here? The product you would expect, remember, this group is going to substitute for the bromine. So this is the product that you would expect. Okay, but notice you get this product. Okay, how in the world am I getting this product? If the bromine was originally here, this is where the bromine was. All right, but somehow, somehow this hydrogen right here moved over to here, and your nucleophile added to this carbon right here to put the group on there. So notice this is the rearranged compound. So we're going to look at why this happens. So carbocations can rearrange to form a more stable carbocation, because notice when the bromine leaves on this carbon, you have a secondary carbocation. But if the hydrogen moves over and you get a carbocation on this carbon, that is now a tertiary carbocation. So that's what's going on. You're forming a more stable carbocation. And you can have what's called a hydride shift or a methyl shift. Okay, this is an example of a methyl shift, where what actually happens first is the bromine leaves and then your methyl kind of pops over. I'm going to do more of this in class. I don't really like these problems that well, so remind me in class to kind of go over these. Okay, that's in a primary case. Yeah, they didn't really do justice here on the. All right, I'm going to do it myself. Here we go. I'm going to explain this scenario right here. I'm going to do it with this, so I don't have to keep drawing the carbons and hydrogens. Here's the bromine. Okay, bromine's going to leave, and you're going to form a plus charge right here. And remember, you have a hydrogen right here. It's this hydrogen I'm talking about. Okay. You have a plus charge right here. Now, what could happen is your nucleophile could come in here, attack, and form your compound. But what actually happens is this hydrogen actually shifts over with its electrons as a hydride shift. And you form, so the hydrogen goes here, and you form now the plus charge, notice, on the tertiary carbon. This carbon is tertiary. This carbon is secondary. This carbon is tertiary. You formed a much more stable carbocation. Now your ethanol comes in here and attacks. Okay, and just does the regular, and then whatever, your bromine comes in and plucks out that hydrogen, or the ethanol. You can have the bromine or the ethanol to form this compound right here, the rearranged compound. Okay. So that's the mechanism. Like I said, remind me to talk about this more in class if you do not understand what I just did there. Okay. And like I said, anytime you have a positive charge, you can have a rearrangement. Okay. You can also have a methyl shift. We'll talk about those in class. All right. So here's kind of a comparison, side-by-side comparison of SN2 versus SN1. Okay. So the smaller, so methyl is smaller than primary, smaller than secondary. Okay, that's the order. Tertiaries, because you could form a tertiary carbocation, is more stable than a secondary. Remember, notice you don't even have primary here. Strong nucleophile, weak nucleophile. Okay. We did not talk about solvents, so don't even worry about the solvent choices. The rate is based on both nucleophile and electrophile. Here, it's just based on your electrophile. You get complete inversion. Here you get racemization. No rearrangements. Here you get rearrangements. Okay, so this is kind of a good slide because it's a side-by-side comparison of the two. Next, we're going to talk about elimination reaction, but I'm going to stop the video here, and we will pick this up on the